non-deterministic Turing machines.
So, hello everybody. So I've been working with Damien and Turlock and Rainer, but they're going to give an hour-long talk about small Turing machines next. So I'm going to do something a little bit different just to keep it interesting. So I'm going to talk about a problem that came about from so I've been working in natural models of computation, so studying models of computation extracted from nature using complexity theory. And the natural computation people use a particular type of model that's a little bit distinct from the normal type used in traditional complexity theory. And that led us to a model of computation that seems to be connected very strongly with OR gates. And we've been trying to characterize the power of this model, and it turned out to be a lot more difficult than we thought, and I'm going to present our work so far on this. And it uses a lot of OR gates. So we're studying the complexity of OR gates, which sounds very simple, but so this represents, I had a nicer picture, but it didn't come out so well, so I found this one, and it's all the different paths all just leading into the same one. So you probably don't need a description of these, but path is the problem where you're given a directed acyclic graph, and there's a node S and a node T, and the problem is true if there is a directed path from S to T in the graph. Parity is the problem is if there's odd number of zeros and ones in strings, and I'm going to be using these two problems a lot. So just to refresh your memory, there's some complexity classes. So P and NP you're probably familiar with, and I'm going to be talking about NL down here, which is non-deterministic log space. So the problem solvable by a log space Turing machine, a non-deterministic log space Turing machine, and the class AC0, which is the problem solvable by constant depth circuits with unbounded fan-in. And I'm actually going to refer to FAC0 because we're talking about functions. So functions that are computable by AND and OR circuits with unbounded fan-in. So the problem arose because there's two types of model. So I should use a picture of the machine that Hassenegger has, but I didn't have a good photo, so I took this one. So that's a Turing machine, and we have one program, and that one program should work for all problem instances. So for example, addition, you can just program your Turing machine and put any problem size on your input tape, and the machine should be able to work on it and output an answer. But if we have a fixed computing device like a circuit, it is of a fixed size, so it can only accept inputs of a certain length. And if you want to compute a problem like addition for bigger numbers, you'll need a bigger circuit. So we need a different device for each size of input. And so we then think, well, if there's no relation between each device for each input size, then we have what's called a non-uniform family. So I'm cheating a bit here. All these, this is an infinite family of computing devices where there's no relationship between each member of the family. So there's just a machine for each member, for each input size. They should all be of the same type of computational model, but I'm cheating just to show the point that we can compute, you can compute, for example, if the nth Turing machine encoded in unary will halt or not with a non-uniform model. So what we prefer instead to work with is a uniform family, where we have one algorithm that describes how to make each member of the family. So given a particular, we want to solve all problems of size 4, the machine that will solve that problem is, there's one algorithm that gives us this similarity throughout all members of the family. So there's a third way of looking at this, which is called semi-uniformity, and this comes from natural computing. So for example, the early DNA computing papers, many of them were semi-uniform, for example those by Lipton. So what this means is that we have a unique machine for every possible input, but there is one function that maps your input to your particular computing device. And whereas uniform in this scheme looks like this, so we have one input, there's one device for each input size. So this particular circuit could work for all inputs of length 7. So let me re-explain this difference between uniform and semi-uniform again. So for example, using a model of computation based on dominoes. So I saw some dominoes upstairs, so I should have made this out. So if we have the problem where we have a maze, and we want to see, is there a path from S to T through the maze? We could just line up our dominoes like this and start knocking it down. And if we knock down the last T domino, then we know there's a path from S to T. But in this is a semi-uniform model, because if we change the maze, then we have to change the way the dominoes are lined up. But if people can also make uniform circuits out of dominoes. So here's an XOR gate in dominoes, and that will work for, so it works correctly for all inputs. So it will give a 1 for, it'll give a 0 for the first and the last input, because the way the dominoes works. But the idea is that it works for all 4 inputs of length 2, and this one will, you need a different machine for each possible problem. And so it was an open problem in for a number of years whether uniform and semi-uniform are equal or not. And for all models that were studied until recently, it seemed to be the case. But it's very easy to find a counterexample, which is when we deal with circuits with only OR gates. So we can say that FAC 0 uniform, semi-uniform families of OR gates is not equal to the uniform equivalent. So that means that, so we can show this by showing that parity can be solved by a semi-uniform family of OR gates, and you just use this classical structure. So we have a row of odd gates and a row of even gates, and if we find a 1 in the input, we change from one row to the other row. So if the number of 1s in the gate was odd, there will be a path from S to T, and if it was even, there won't be a path from S to T. So that's a semi-uniform family to accept parity, but we can then see the parity is not in uniform OR, because we can think of an OR circuit as just like a big collection of OR gates, and we can just replace that with a single OR gate. So if if parity was accepted by a uniform OR circuit, then OR would be equal to XOR, which would be, so we can see that semi-uniformity and uniformity are not the same. So what are we've found that this is a counterexample to the conjecture that uniformity is equal to semi-uniformity. So what is the actual power of these two classes? So let's start with semi-uniformity. And we found that this class is equal to NL. And we proved this by using the path problem. So we're given an instance of path. So we have a directed acyclic graph and nodes S and T, and we can just change those into, we can very easily turn that into a OR circuit, such that there is a path, and we have a constant gate, and that constant gate flows through the circuit to the output gate, and the circuit will say yes if there is a path, and then we can so then we've seen that there is a path problem in the OR circuit, and we can we can simulate the OR circuit in non-deterministic log space by adding an S node to each of the 1 inputs, and then there will be a path from S to T if that accepts. So we've shown this. This is an old result, and so that our old result. Semi-uniform OR is equal to NL. And so now, what about the uniform version? So this is a slightly more subtle problem, and I'm going to tell you the best result we have so far. So in this case, we have one OR circuit that's going to work for all input lengths. So we think about using our other technique, which is we can think about just taking a single OR gate and trying to replace that whole big OR circuit with a single OR gate. So we could try just wiring up each input gate up to the OR gate, but then we don't know how do we know that this input gate is in fact on a path to the output? And it turns out that we can't know this, and this is another path problem, and that we need to use some non-deterministic Turing machines in here. So the graph here on the left-hand side is defined entirely by the length of the input. So given the width of the input, we can then construct a graph, and a non-deterministic Turing machine can decide if there is a path from the input to the output. Okay, so the way this works is we need so Turing machines that have their input tape restricted to only ones are called tally Turing machines, and we want to give each one the reachability problem of, given this graph and this particular input gate, is that input gate connected to the output? So we can we have an AC0 circuit that takes the length of the input and encodes it with an input gate and feeds it into the tally NL machine, and he will give a 1 if that gate is connected or not. And if the input bit is 0, then it will say 0. So this corresponds to something called a truth table reduction, and it's a deterministic the disjunctive truth table reduction, because we have a single OR gate at the end. So our best upper bound at the moment for uniform OR circuits is those that are disjunctive truth table reducible to tally NL. So what about the lower bound? So we've seen how it seems like there's a reachability problem encoded into the structure of the circuit. So if we're given we try and exploit this. So we try and think of the hardest problem, or a problem that exploits this the most. So we take a tally Turing machine, a tally NL Turing machine M, and we construct the configuration graph for that machine on some particular input X, and so the configuration graph. You probably know what this is. So it's you take all the information, the instantaneous description of the Turing machine, so the position on the input tape, the work tape, the state it's in, and if on this particular input you can go from one configuration to another, then you add an edge in this graph, and because it's log space, that will be of polynomial size. So you make a reachability problem out of that single unary word, and from this we can modify that function and instead create an OR circuit, so that to satisfy the definition of OR circuits, we have to put some input gates, but we can ignore those, and we just put a single constant gate, which, if that particular Turing machine accepts, there will be a path from the initial configuration to the accept condition, which we label the output gate here. So from this we can see that the uniform OR circuit can accept all the problems in tally NL. And we can then say it's a strict inclusion because the AC0 uniform OR circuit can accept some binary words, whereas the tally one is a tally language. So then we can think, well, what if we think about a slightly stronger claim? What about all the words that are reducible, many one reducible to tally NL? And well, we can't solve those because there could be, for example, an AND function in the reduction. So here is our view of the world. So while trying to characterize uniform OR circuits, our best lower bound is tally NL. Our best upper bound is disjunctive truth table reducible to tally NL, and we're trying to see how much if we can improve on that at all. So in future work we want to examine some different types of gates and what happens when we when we put in some different types of gates into that system. We've nearly completed the same graph for AND circuits and figured out the relationships between them. For NAND gates, it's simple that it's equal to P. And so we thought, was this something to do with monotone gates? But and so the next step will be to see what happens when we use XOR gates. So in summary, semi-uniformity is uniformity is weaker than semi-uniformity, and this result applies to all types of computation that use families. And so for future work we want to exactly characterize uniform OR circuits, and we're going to examine some other gates. So thank you very much, and any questions? Okay.